You'd be like, oh, so you gotta pose a little bit. I'm just
Oh, you
joking.
mean video, you mean? Are you kidding, really?
Yeah, or I'll just.
Oh, you actually want to, like, video record? Oh, you want to get that, not me.
Yeah. No.
Yeah, thanks a lot. So you don't care about me, it's on the screen, huh? Okay, anyway, okay. You really know how to make a guy feel good. Okay, so, okay, so can we say either of those two variables the cause of the other?
No.
Well, no, correlation does not imply causation. Yeah, most of you got that, yeah. So just because two quantities can be very highly correlated, but that does not mean that one causes the other, or that there's any relationship between the two at all, other than the fact that they kind of go, they seem to go together. Yeah. Okay. So section 2.2. I'm not sure if we want to do that one. That might just be just a histogram or something like that.
Yeah, I don't think you want to test us on that either.
I think you know how to do it.
Yeah.
Let's skip that one. How about we go to 3.1?
Wait, so histograms will not be on the exam, right?
No, you should know how to make one. I don't want to just want to go over it now. It's kind of a waste of time.
Histogram.
Let's see, 3.1.
2.4 is when
Maybe
you
you're gonna have
actually
to
solve
post
the
on YouTube.
equation.
3.1, 6, 9, 12, and 18.
Just making sure.
Yeah, well, this is like mean, medium, mode. You know how to find those, right?
Yes.
Okay, let's get that. So 6, 8, 34, and 3.2. Yeah, that's finding the standard deviations. You know how to find those too. So let's skip that one.
Do we?
3.3.
To be honest,
okay, yeah, 3.3 might be a good one. So number 8.
okay, I know this might sound funny, but
Yeah.
I still get confused as far as what X bar is.
X bar is a sample mean.
X bar is the sample mean.
Yeah, mu is the population mean. X bar is a sample mean. Mu is population, yeah. Yeah, mu is population. That's why on that the female pulse rates, it was mu.
Mm-hmm.
But yeah, we had a sample of whatever number of women from each of the populations, but we were interested in determining whether the population pulse rates were equal.
Why did you circle our M's?
Sorry, it's mu, not m.
Oh, okay, so we have to make it.
Little mu. Yeah, mu.
Has to
Yeah,
be that.
mu means population meaning.
Not M.
Let's see.
So you have to do an M. Can't do an M.
Do we want to do those? Okay, how about number 10? 10's a good one, I think. MCAT scores.
For 3.3?
Yeah, 3.3, number 10. In recent years, scores on the medical college admission test had a mean of 25.2 and a standard deviation of 6.4. Identify the MCAT scores that are significantly low or significantly high. Well, you can see here, you compute, if you have a z-score that's either below -2 or above 2, that's considered significant. So find the z-score values, find the values that are, that are beyond 2 z-scores or below 2 z-scores.
What's the Z?
Or below, below.
One more time?
Yeah, sorry, let's say that one more time. So you can read here. So a value is significantly low if its z-score is -2,
Or
less than or equal to -2. It's significantly high if the z-score is greater than or equal to 2.
okay.
Well, a z-score of 2 means 2 standard deviations. Right? So simply this plus 2 of these, a score higher than that would be high, and this minus 2 of those below that would be significantly low. Because one z-score is like one standard deviation. One standard deviation above the mean has a z-score of 1. 2 standard deviations above the mean has a z-score of 2. Or if you, sorry.
I was gonna say, would we use the Z table for these?
No, you don't. No, you're just finding. You don't even know the distribution. No, you don't need to. So, or you can just solve this equation. Here, solve this equation. So solve
Is it X minus
2 equals, X bar minus, what do we want? We want 2 is equal to, sorry. What's mine? Yeah, yeah. Okay. Here, for specifically for this problem, 25.2 minus x over 6.4.
We don't start seeing.
Oh,
Okay, so that's a z-score, that's the upper z-score, z-score of 2. Remember, it's the mean minus your value divided by the standard deviation, x minus mu over sigma. Or you could do it the, actually, sorry, the other way around, sorry. X minus 25.2 over 6.4. Yeah, so solve that for x, and that's then that's the z-score beyond which the numbers are significantly high.
And so what you do
It's
is
basically 2 standard deviations. 2 standard deviations above the mean. 2 standard deviations above the mean has a z-score of 2. So you get every z-score number is 1 standard deviation. Z-score of 1 standard deviation. Z-score of 2 standard deviations. Z-score of 3 standard deviations. And similarly, -1, -2, -3. So again, you can use this formula. So if you solve here, so you get 2 times 6.4 equals x minus 25.2. So x is equal to 25.2 plus 2 times 6.4. So 25.2 plus 12.8, which is 38. So an MCAT score of 38 or above would be considered significantly high. And now do the same thing for -2. Yeah.
And then, when you find both of those numbers, do you have to write a sentence explaining this?
Well, identify that are, yeah, you'd say, well, you want to identify which is which. Well, okay, yeah, you want to write something. Identify the scores that are significantly low or significantly high. So you would say anything 38 or bigger is significantly high. Yeah, you would have to write that. Anything that's, anything that's 23 or lower would be significant. Anything that's below the low would be significantly low, yeah. It's not just 38, yeah, 38 is significantly high, but so is anything higher than that. This is a rule of thumb for determining whether or not a data value is significantly high or low, without even knowing the distribution, by just looking at the z-score. So the other one would be, so -2 equals x minus 25.2 divided by 6.4. So -12.8 is equal to x minus 25.2. So x is equal to 25.2 minus 12.8. 6, 4, 2, is that 22.6?
I got it.
Oh, sorry, 22.4, right?
No,
Sorry, can't say,
12.4.
12 minus 12 point, 12.4. Oh, it's 4, really?
That's the answer.
Oh, the answer is 12.4? Oh, thank you, okay, thank you, yeah, 12.4, thank you, the answer, okay, there we go. Okay, so your answer would be anything below 12.4 is significantly low, anything above 38 is significantly high. Yeah. Okay, remember that now?
Yep.
Okay, good, you remember. Okay, so if you look at number 14, it's kind of the same idea. Use z-scores to compare the given values. So you can use z-scores to compare which value, even in different data sets, is more extreme. So here you have 2 populations. You have males and females. Okay. Males have a red blood cell counts that, females that and that. Okay, so who has the higher count relative to the sample from which it came? A male with a count of 5.58 or a female with a count of 5.23. So how do you do this?
You do
Find what?
the value.
The z-scores for each of these values, and then which z-score is bigger. That one's the more extreme one.
And you just plug it into the.
Yeah, use the z-score formula.
Oh, z-score formula.
Yeah. Yeah.
Z-score
Z is
formula.
equal to x minus x minus mu over sigma.
I can't
Okay?
find it.
It should be in your, it should be there. It should be there.
X minus X bar over S.
Where is it?
Oh, this one?
Yeah, it's just not written in variable.
Oh, I see, okay.
Wait, no, I don't see it.
It's there.
Where?
It's there somewhere. We're in chapter 3. It's probably there somewhere. Where is it? Actually, it's in chapter 6 is the z-score formula. Yeah, he uses it for the normal distribution too. Yeah, I don't know why he didn't put it in chapter 2 or in chapter 3.
Normal?
Anyway, it's in chapter 6, yeah.
Oh, X
so
minus X over S.
For the final exam, are you going to give us the entire, formula?
Well, everything you need. Well, you're gonna get the same formula sheets, because there's nothing, because the formula sheets I gave you have all this stuff. Yeah, chapters 3 through 12, these two, and then that, and then is the, yeah, what I gave you for the exam. It was all they were all there.
Okay.
Okay, so which one's more extreme? Let's see. So male, 5.58. So 5.58 minus 4.7919 divided by, so 5.58. 4.719, subtract that, divide by 0.49. Okay, so the male has a z-score of 1.76, rounded to 3 digits. The female,
2.19.
okay, let's see. Yeah, 2.19. So who has the more extreme? The male or the female?
The female.
The female, yeah, because she's got the higher z-score. The more extreme z-score, I should say. It could be more negative too, but yeah. Yeah, so it's a female. Yeah.
So what you did was you took the count that they have, right, 5.58
Right.
or 5.23, and then you subtracted the mean from that.
Right, yeah, just basically found the z-score of each of those numbers,
And then you divided it by
the standard deviation, yeah, so z-score equals x minus mu over sigma. Okay. Yeah, this is not just used for the normal distribution. See, we're using it here too. You can compute the z-score of any data value, but for the normal distribution, it has special significance. But you can do it with any data value. Just subtract its mean, divide by standard deviation. Okay? And it allows you to do like what we did here, you know, compare the relative standing of data values within 2 different data sets. That's what we're doing here. Okay? The relative standing of a male with 5.58 versus the relative standing of a female with 5.23. It turns out the female with 5.23 has a more extreme count than the male of 5.58 because it has a higher z-score. Yeah.
So for this section, are you gonna ask us for definitions too? Like to
Yeah.
define what a z-score
I
is?
don't do definitions.
I like
We
that.
didn't know that. No, I don't do that.
For the first test we had to.
Oh, really? Yeah, no.
And why?
Well, I mean, like, well, you had that problem, is it discrete or continuous data? I'm not gonna ask you to define discrete or continuous, but you feel recognize it.
Oh,
So, yeah, so, you know, I'm not big on. Okay, let's see. Where are we, 3.3? I think the other ones are just more, kind of more of the same. Let's move on. Let's move on. How about section 4.1? (23) and 25 on 4.1. Okay.
4.1?
Yeah, let's move to 4.1. Yeah, we only have a few minutes left, so, well, I think the best thing to do to refresh your memory. Okay, so number 23. Find the probability, so so here's a two-way table. Probably looks familiar from section 11.2. Okay, we could do a test of independence on that now. But not that we're not going to here. Find the probability of selecting someone who uses drugs from that. We got 555 subjects. So the total of all those numbers is 555. If someone from this sample was selected at random, what would be the probability that they use drugs? Well, it would be, well, here, how many people use drugs? 45 plus 5, yes, so 50 out of 555. That would be the probability. Yeah,
Which one was this? I'm sorry. I don't.
23.
23.
Yeah,
And so would we just write that as the answer?
yeah, that's it. 50 out of 555. That's the probability. Yeah. Okay.
And so if we
Yeah.
wrote that in fraction format, would that be acceptable?
That's fine. You don't need to simplify.
Okay.
Either way. We could skip 25, that one's pretty simple. How about 4.2?
Yep.
35. They're pretty basic. 35, 9. How about number 9? If an order is selected, find the probability of getting food that is not from McDonald's. So given that table.
So here you use the complement.
Yeah, you use it, right, you can do it directly. So not from McDonald's, first of all, you gotta add all these up. Okay, so not from McDonald's, you would add up this column, and that column, add those all together, divide by the total for the table. That'd be the direct rate. Or you can use the complement rule. The probability of not from McDonald's is 1 minus the probability of McDonald's. So the probability of not McDonald's is 1 minus the probability of McDonald's. Okay, which is a bit easier to do. So that would be, you would take these two, add them together, divide by 555, and subtract from 1. So complement rule.
1118.
Yeah, whatever, yeah. Or sorry, 1118, yeah, whatever the total is for that table. Okay, so this is the complement rule. So we want to find the probability of one of these is selected at random, one of the orders is selected at random, not from McDonald's. So you can do that directly, add the Burger King, add the Wendy's, add the Taco Bell, add all those together and divide by the table total, which is 1118. Or you can use the complement rule. The probability of not McDonald's is 1 minus the probability of McDonald's. Add those two together and divide that by the table total. Subtract from 1. Yeah, complement rule. Okay? Yeah, okay, you got it. Okay. Let's see. 22, 9, 15. Oh, let's see, let's do good number 21. It's more useful, I think, right now. So here the hint is construct the table. So this is testing for marijuana use. 143 subjects with positive test results, 24 are false positive. Among 157 with negative test results, there are 3 false negatives. Okay, so let's look at that. Here, let's construct the table first. So use or not use marijuana, test positive, test negative. 143 subjects have positive test results. So where do they go? Well, that's a total of these two, so we're gonna put that here. 143 are positive, regardless.
137 negative, so.
Yeah, and 24 false positive. So false positive means test positive but not used. So 24 is here. So find that one. Find use and test positive. How are you gonna find that entry? Subtract from 143, yeah. 119. Okay. 157 negative results, where do they go? Right here, total. 3 false negatives. So false negatives means use and test negative. 3 up here. A false positive is, let's see, a false positive is not use and positive. A false negative is use and test negative. Where the test gets it wrong, basically. The test gets it wrong. Okay, there's 2 cases where the test can get it wrong. For a user who tested negative, or for a non-user who tested positive. Those are the 2 cases where the test can get it wrong. Okay, so how many test negative and not use? 154. Okay, so now we have the table. Now let's answer a question. Let's see. 4.2, 21, 21. Okay, so how many subjects are in the study? How many subjects are in the study?
300?
Yeah, well, how are we going to find how many are in the study? Add them all up. But we could add these 2 actually.
Yeah.
Because it's going to be, what, 200, not, yeah, 300. So 300 in the study. How many subjects had a true negative result? A true negative. In other words, didn't use and test negative. 154, yeah. So a true negative, again, true negative means the test was correct, they didn't use and they test negative. So 154. What is the probability that a randomly selected subject had a true negative result? What is the probability? So now you just have to find the probability of that. What's the probability that a randomly selected subject had a true negative result? Well, that would be
Probability
of 154 over 300. Yeah. Yeah, the number is 154, but the probability will divide that by 300. Okay. Let's see, 4.223. Okay, let's look at 23. If one of the subjects is selected at random, or randomly selected, find the probability the subject tested positive or did not use marijuana. Okay, so here you can use the addition rule. Or you can look at it from the table or do it this way. So the probability tested positive or did not use. So this is an or, this is equal to the probability of test positive plus the probability doesn't use, or didn't use, minus the probability test positive and doesn't use. Okay, so recall this is the addition rule. Now it's easier just to get it directly off the table. Okay. So what's the probability? Or let's find the people who tested positive. Where are they? Here. let's find the people who did not use, they're here. So we just add all these up and then divide by 300, but you don't want to count 24 twice, you just count it once. So 119 plus 24 plus 154. See, if you do it this way, the number that tested positive is 143 divided by 300 plus, what's this, 178. 178 over 300 minus 24 over 300. See, if you just count, if you find the probability of testing positive, which is 143 over 300, plus the probability it doesn't use, 178 over 300, you've counted these 24 twice. So that's why it's subtracted here. But if you go directly from the table, then you won't count it twice. So just the 119 plus the 24 plus the 154.
You could also do 1 minus 3 over 300, right?
Yeah, actually, that's a good point. Yeah, you could use the complement rule here. Yeah, good point. Good point.
1 minus what?
1 minus 3.
Oh,
Yeah, because that's all that's left in the table. Yeah, yeah, 1 minus 3 over. Yeah, that'll work. Good observation. Okay. 24. If one of the subjects is randomly selected, find the probability the subject did not use marijuana. What is that?
should it be 178?
178, that's 178, yeah. If one is selected at random, the probability they don't use, so we're ignoring the test positive or negative, it's just the sum of these two over 300. Okay? Okay. Let's see, 4.3. Conditional. 5, 7. Let's look at number 5. Or actually, look at number 7. Complement rule in action. In the United States, the true probability of being a baby boy, of a baby being a boy, is 0.512. Among the next 6 randomly selected births in the United States, what is the probability at least one of them is a girl? Okay, so now you can do this the hard way, or you can do this the easier way. The hard way, you should do it directly. Let's write this out with some notation. So the probability that at least one girl. Okay, of course, in 6 births. Well, we'd have to find the probability of 1 girl, 2 girls, 3 girls, 4 girls, 5 girls, or 6 girls. But that's the hard way. What can we do instead?
Square.
You can
Yeah, the probability of at least 1 is 1 minus the probability of
all boys.
All boys.
none. Yeah, no girls, all boys, yeah. No girls. Which is all boys. And that's easy to compute. Okay, so we can assume these are independent, these births, okay, different people and all that, different locations, not related. So find what's the probability of all boys? Well, that's, yeah, 0.512 to the 6th power, yeah. Yeah, these are independent. We can do that because they're independent. 0.512 to the 6th power. So these are independent. Yeah, when you have independent events, the probability that they all happen is just the product of the individual probabilities. Okay. Let's see. 7, 11, how about that? Let's do number 11, similar problem. Okay. It has been reported that 20% of iPhones manufactured by Foxconn for a product launch did not meet Apple's quality standards. An engineer needs at least one defective iPhone so she can try to identify the problem. If she randomly selects 15 iPhones from a very large batch, what is the probability she will get at least one that is defective? Well, when you see the words, when looking at probability, and you see the words at least one, think of complement rule.
Yeah.
Okay, at least one, because particularly if it's a large number, you know, at least one, think of a complement rule. So the probability at least one defective is equal to 1 minus the probability of?
All defective.
No,
What? No defect.
no defective. So we'll assume these are all independent events. So what's the probability of no defective in 15 selected? Well, what's the probability of any one iPhone being defective?
20%. So
I should say, yeah, the probability of one iPhone being defective is 0.2. What's the probability of it not being defective? Because that's what we need.
0.8.
Yeah, 0.8, but now there's 15 of them, so 0.8 to what power?
To 15.
Yeah, 15 power. Again, and then we treat these as independent. Okay, so the probability of at least one defective in 15 is 1 minus the probability of no defective in 15, which means all good iPhones. So 0.8. Probability of selecting a non-defective. So this is 1 minus 0.8 to the 15th power. Okay? Yeah, 0. Let's see, yeah, 0.965 is the probability. So she's got a pretty high probability of getting one in the 15. Okay, any questions on that one? Number 11. How about number 13? So the denomination effect. So students were given either 4 quarters or a dollar bill, and it was determined whether they want to keep the money or spend it on gum. And here's the result. So find the probability of randomly selecting a student who spent the money given that she was given 4 quarters. Okay, so when you see the word given that, it's conditional probability. So we want to find the probability of spend given that 4 quarters. Okay, so we know that she got, he or she, we know that this student got 4 quarters. That's given. Okay, that's given. The only question is spend or not. So when you have a given, when you have a conditional probability like this, it really reduces your table because we can get rid of the second row of the table because we're only concerned with people who have been given 4 quarters. So we ignore the second row. So of the people who have been given 4 quarters, what's the probability they spend? Well, that's going to be the number to spend. What's that? 16 divided by the total number given the 4 quarters.
Mm-hmm.
Okay, so that's 16 over 27 plus 16. Okay, so these conditional probabilities, they reduce your sample space. Okay, we're not dealing with people who were given a dollar bill now.
Wait,
We're given with, did I make a mistake?
No, spent or be purchased from, not kept.
Spent the money, give, oh, sorry, 27. Yeah, thank you, 27. Thanks.
You're thinking of the next one.
yeah.
Okay,
Go
there,
ahead.
27, okay. Are we on problem? Yeah. Oh, okay, yeah, thank you. Yeah, okay. Yeah, that's the second one. So spent, given 4 quarters, 27 over 14, or 27 over 43. Okay, part B, kept given 4 quarters, that would be 16 over. Yeah.
Or just subtract.
Or just subtract, exactly, complement, or just subtract that from 1, yeah. So the probability of kept 4 quarters. 16 over 27 plus 16. I'll forget part C. Okay. Do you want to do another one of these or not? Yeah. Not that, let's record the number. Let's see.
Chapter 5.
Yeah, let's see. No, we're not gonna do anything more in chapter 4. Let's see. Oh, yeah, how about this one? Number 23 on 4.4. The company needs to appoint a president, chief executive officer, chief operating officer, chief financial officer. Must also appoint a strategic planning committee of 4 members. There are 10 qualified candidates, officers can also serve on the committee. How many different ways can the officers be appointed? Well, think of each of the positions. Here, I think it'd be useful to think of this way. You've got the president. You've got CEO. You've got the COO, a who and a who, yeah. The CEO, a COO, and a CFO. So if we start with the president, how many different ways can a president be chosen from 10 people?
10.
10. And how many are left? Assume they can't hold, no 2 people, nobody can hold the same, nobody can hold more than 1 position. How many left for the CEO?
9.
Yeah, so this is like a permutations problem, really. Because, I mean, not told that order matters, but in the sense it does. Because these are specific positions.
So 10.
Remember, the difference between permutations and combinations. In permutations, order matters. In combinations, it doesn't. Okay, now, B, how many different ways can a committee of 4 be appointed? Well, does the order matter here? No, it doesn't. So that would be, using the notation, C, 10, 4. Okay, 10 choose 4. Um, 210?
Yep.
Yeah, 210. So the committee can be chosen in 210 different ways. The committee of 4. Order doesn't matter.
This is everything else.
10 choose 4. Yeah, because the officers can also serve on the committee. Okay. Any other, any other questions? Do the last one. What's the probability of random selecting committee members and getting the four youngest of the qualified candidates. What would that be? Well, how many committees have exactly the four youngest? One of them. So what's the probability of selecting committee that has the four youngest? Yeah, one out of the two candidates, yeah, weren't you? Yeah.
So our final is Wednesday, right?
Yeah, so I'm thinking, I don't know if there's any interest, okay, I was thinking maybe, I don't know if you wanna do like an extra review session, maybe